Welcome to The Explainer. Today, we are talking about a really fundamental shift in how computers see the world. We're going to get into how computer vision is finally moving away from these clunky, handcrafted rules and towards a much smarter approach called end-to-end learning.
So here's the question at the heart of it all. How does an AI look at a crowded scene and tell all the different objects apart? I mean, this is one of the toughest challenges out there, and for a really long time, our solutions were, well, they were kind of clumsy. Now, to really get why the new way is such a breakthrough, we have to look at the problem that older models, like the famous YOLO architecture, used to run into. They were powerful, for sure, but they had this little habit of being, let's just say, a bit overeager.
Imagine you tell an AI, hey, find all the people in this photo. An older model might go and find the exact same person 3, 4, maybe 5 times, drawing all these overlapping boxes around them. And you end up with this total mess of an output that's not really useful until you do some serious cleanup.
So how do they fix this? Well, they tacked on this separate, handcrafted step called non-maximum suppression, or NMS. And its job was pretty simple. Just look at all those overlapping boxes for one object and delete the extras. It was a blunt tool, but for a long time it was what we have.
But here's the kicker. That simple rule falls apart in really crowded scenes, right? You get a bunch of people packed together and their boxes are supposed to overlap. NMS gets confused by this, and it can start deleting the correct boxes, making the model miss things it actually found.
And you know, what's so wild about this is that having to rely on NMS completely went against the spirit of modern AI. The entire point of deep learning is to let the model figure out the complicated stuff from the data itself, not for us to jump in at the end with these rigid, breakable instructions.
Okay, so that brings us to 2020. Researchers at Facebook AI come along with this totally new philosophy called DETR, which stands for Detection Transformer. And they basically decided to just throw the old rulebook out the window.
The whole goal with DETR was to build something more elegant. A system that just gets rid of all those extra, clunky, handcrafted pieces and just lets the model do its job from start to finish.
The core idea was to completely reframe the problem. So instead of, finding a bunch of stuff and then cleaning up the mess later, DTR treats object detection as a direct set prediction problem. You feed it an image, and in one single shot, it outputs the final, clean, perfect set of objects. No duplicates, no post-processing, no cleanup required.
So, how on earth does it actually pull this off? Well, the magic here is really in 2 key ingredients working together. The incredible transformer architecture and a really clever way of teaching it called a loss function. First up, transformers. The thing that makes them special is a mechanism called attention. Honestly, the best way to think about it is like you're at a super loud party. You can somehow tune out all the background noise and just focus on the one conversation you're having with your friend. That ability to focus, that's attention. Now, for an image, this means the model can see how every single pixel relates to every other pixel all at the same time. This global context is the absolute secret sauce. Because the model sees the entire picture at once, it just understands that 2 possible detections are really just the same object, so it doesn't even bother making duplicates in the first place. But look, a smart architecture is only half the story. You have to train it the right way. And for this, DTR uses this totally unique approach called bipartite matching loss. You can think of it as a kind of perfect matchmaking algorithm. So, while the model is training, this matchmaking algorithm is constantly comparing what the model thinks it sees with what's actually in the image, and it forces a strict one-to-one pairing. So if there are 3 real cars, the model has to predict exactly 3 cars. If it predicts a 4th one, that extra prediction gets matched to a special no-object class, and the model gets penalized for it. It's this brilliant trick that forces the model to learn not just what to detect, but also how many. Okay, so DTR was a fantastic idea, a real paradigm shift. But there was a catch. That global attention thing, where every pixel talks to every other pixel, it is incredibly computationally expensive. The problem is that the complexity scales quadratically with the number of pixels. That's the n squared you see here. What does that mean? Well, if you just double the height and width of your image, you get 4 times the pixels. But the computation needed becomes 4 squared, or 16 times more difficult. This was a huge problem for high-resolution images, which you absolutely need if you want to find small objects. And this is where deformable DETR comes in with an absolutely brilliant solution. Instead of using a giant floodlight that has to light up every single pixel just to find what's important, deformable attention is more like a smart spotlight. The model actually learns where the most interesting parts of the image are and focuses all of its attention on just a few key points.
And the results? They speak for themselves. The model trains way faster, it's so much more efficient, and crucially, it gets a lot better at spotting those tiny little objects that the original DETR really struggled with.
So let's just zoom out for a second. Why is this such a big deal? This is about more than just a better model. It's about a whole new way of thinking about how to build AI.
You can really see the evolution here on this timeline. We went from these messy pipelines that needed us to come in and clean things up manually, to the beautiful end-to-end idea of DETR. And now, with deformable DETR, that amazing idea is finally efficient enough and powerful enough to be truly practical in the real world.
At the end of the day, this whole thing represents a really fundamental shift. We're moving away from building systems that just follow our simple, often flawed rules, and we're moving towards creating AI that can learn for itself the best, most effective way to solve a problem.
And that leaves us with a really exciting question. This idea of a learned, dynamic focus, of an AI that learns not just what to see, but where to look. That opens up some truly incredible possibilities for the future of artificial intelligence. Thanks for joining me for this explainer.